Hey everyone, thanks for being willing to do class this way, and I hope this is a helpful walkthrough of some of the basic meanings and really simple translations of quantifiers and uh, quantified formula in our new language, predicate logic. So in class last week, we learned the English meanings of unquantified formula in QL in our new language. So here on the left-hand side, we have a few such unquantified formula. We have FC, FE, FC, and OC, and then FC, if FC, then MC. And in the top right corner, you've got your scheme of abbreviation. So pairing these up with our scheme of abbreviation, what does capital F lowercase c mean? It means copper is a dog. Lowercase c is our name letter. Capital F is the predicate is a dog, and so we've got capital F predicated of the name letter C. Fe, Ollie is a dog. Third, we've got a conjunction there, FC and OC. Copper is a brown dog is one way of translating this. You could also translate it, copper is both brown and a dog, or copper is both a dog and brown. More naturally, being a brown dog is the way we would put that in English, but in terms of right or wrong answers for logic translations, copper is both brown and a dog works perfectly fine. And the conditional down there at the bottom, if copper is a dog, then he's a mammal. So those are really straightforward, right? But at the end of class, we introduced quantifiers to our stock of resources. And quantifiers can look a little bit intimidating at first. And those simple translations of unquantified formula, if you got comfortable with those, you might be kind of thrown off by the addition of the quantifiers. So we're going to walk through those today. Here are some really simple rules. What does the universal quantifier sign, the upside down A, what does that mean in English? Well, roughly it means everything is such that. So the universal quantifier generalizes over everything whatsoever. Another translation for the universal quantifier is all or every. And the such that is going to be filled in by further statements describing ways that everything whatsoever is. So for all x, fx is saying everything is such that it is f, where here the predicate f means is a dog. So the obviously false claim, everything is a dog, is the way we translate that in English. So here is a quantified formula. For all x, mx would be how you'd read that in predicate logic. And in English, when we match that up with our scheme of abbreviation, we translate that everything is a mammal, right? So here we've got M is our predicate. And the X there you can think of as a pronoun. What it's saying is, for anything whatsoever, it is a mammal. That's what the X is doing. It's it's functioning as a pronoun. So sometimes what I'll do is introduce a kind of intermediate way of speaking and thinking that's in between the straight up symbolic predicate logic sentences, the formula, the quantified formula on the one hand, and English on the other. And I'm going to call it quantifier ease or QLEs. And this is sort of a very circuitous and awkward English. But what it's doing is just helping you to see the transition between the purely symbolic language and their English translations. So in quantifier ease, this sentence says, for any x, for anything whatsoever, that x, is a mammal. Okay, so secondly, we've got our existential quantifier sign, which means roughly something is such that, where the such that is going to be filled in with predicates and variables, and occasionally name letters, as we'll see later. So suppose you have something. So suppose you have something is m, or in quantifier in the symbolic language, there is some x such that x is m. How would we translate that? Well, in English, what this is saying is not everything is a mammal, but something is a mammal. It's general in that it doesn't name any particulars, but it's not so general as to encompass everything whatsoever. Instead, it just says there's something or other, we don't know what it is, that is a mammal. So in quantifier ease, the bridge language between English and our symbolic language, you can think of this sentence as saying there is something such that that something is a mammal. Again, right now you may not see the utility of quantifier ease, but as these become more complex, I at least find it helpful to have the quantifier ease bridge in my mind, and that helps me complete the translations correctly without mixing up what is being attached to what quantifier. So here's some more complex cases. So this sentence says there is some x such that x is f and x is m. What is this saying in English? Well, in quantifier ease, we'll start there. Something or other, we don't know what it is the following way. That thing, both is a dog and a mammal. So when we look up to our schema here, obviously dog and mammal are our predicates, and the it is going to be our x, it's corresponding to the variable there. The and is the caret, the conjunction sign, and the something is our quantifier. So what is this asserting, this quantifier ease? More naturally in English, what it's saying is something is both a dog and a mammal. Another equally good way of translating that is some dog is a mammal. Another equally good way of translating that is some dogs are mammals. Yet another equally good way of translating it is many dogs are mammals, or a few dogs are mammals. And there, notice that what's going on is that our existential quantifier, while helping us to capture more fine-grained logical detail in English, there's some fineness of grain that even the existential quantifier is insensitive to. And here, the quantifier does not distinguish between some, many, a few, a handful. As long as you have at least one thing that is both a dog and a mammal, it may be half of the things are both, it may be two, it may be very many, or it may be very few. As long as it's some of them, and one will do the trick, that is what that sentence on the left-hand side is asserting. Some dog is a mammal. Okay, here's one with a universal quantifier, and it's got an arrow in it, so it's got a conditional. Notice that those brackets there are bracketing the conditional, but not bracketing the quantifier. So what this tells you, I mean, in the previous case, you had similar brackets. What this tells you is that the quantifier on the outside is operating on everything on the inside of those brackets. So when a quantifier abuts a bracket, it operates on everything inside the bracket until you hit the next closed bracket. So here in quantifier ease, this is saying everything whatsoever is such that if it's a dog, then it's a mammal. And that's a little bit awkward. Everything is such that if then. What does that mean in English? Well, in English, we translate this as every dog is a mammal. Now you might be like, wait a second, I thought that the universal quantifier captured everything. And now we just have every dog. Well, that's not all the things. I mean, this thing of liquid is not a dog, so is the quantifier ranging over that as well? And the answer is that it is ranging over everything whatsoever. But because what's on the inside there is a conditional, all it's telling us is that for everything whatsoever, each and everything meets the following condition. If it's a dog, then it's a mammal. So it's even true of me that if I'm a dog, then I'm a mammal. It's true of this thing. If it's a dog, then it's a mammal. It's not a dog. But that's okay. For all of the things, my dogs are sleeping over there. It's true of them that if they're dogs, then they're mammals. Since they are dogs, they also are mammals. So the way we capture this is that everything that is a dog is a mammal, or all dogs are mammals, or everything that is a dog is a mammal in English. Okay, so these two basic complex formula here are really important to start memorizing. You're going to encounter a lot of existentially quantified formula that have conjunctions on the inside. And you're going to encounter a lot of universally quantified formula that have conditionals on the inside. That's because they naturally correspond to something is both this and that in the first case, and everything that is this way is that way in the second case. It's really important not to confuse a universally quantified conditional. So in this case, on the left-hand side, you have universal quantifier, if fx, then mx, or for all x, if x is f, then x is m. We translate that as every dog is a mammal. It's really important not to confuse that with the conjunction version, a universally quantified conjunction. For any x, x is both f and x is m, which in English we translate as everything is both a dog and a mammal. And that's a different claim from every dog is a mammal. The first claim is true. It is indeed true that every dog is a mammal. In English, the second claim is false. It's not true that everything's both a dog and a mammal. Lots of things are not dogs. I'm not a dog. Lots of things are not mammals. This is not a mammal. Lots of things are neither dogs nor mammals. So universally quantified conjunctions are rarer. You may still encounter them at some point. When doing translations, though, it's really important not to confuse for all x, if x is f, then x is m, with for all x, x is both f and m. Logically, they're saying different things. Likewise, it's really important not to confuse there is some x such that x is both f and x is m, or something is both a dog and a mammal, with a conditional version. There is some x such that if it's a dog, then it's a mammal. The first one asserts there really is something that both has the feature of being a dog and has the feature of being a mammal. The second one doesn't actually assert much of anything at all. except a conditional relationship. It doesn't tell us whether anything actually is a dog or whether anything actually is a mammal. It just says that if it's a dog, then it's a mammal. Well, are there any things that are dogs? Doesn't say. Whereas the first one does. We're going to come back to that and talk a little bit more about the potential pitfalls there and do a little bit more of the truth tables for conjunction and conditional to justify why they have to be treated differently. Okay, so let's talk a little bit about the truth conditions for quantified formula. So here we have for all x, if x is f, then x is m, or every dog is a mammal. Under what circumstances or under what conditions is this quantified formula true, and under what conditions is it false? This is going to become important later when we build countermodels. It will be useful to know the truth conditions for these when you do derivations with them. But even more basically, just getting you to understand the relationship between universally quantified statements and what are called particular instances of that statement is going to be useful in your translations. Okay, so in order to figure out whether this is true or false in a particular universe or world of objects like ours or some possible one that we're imagining, either way, remove the universal quantifier is your first step. You're like, is it true that every F is an M, that every dog is a mammal? Well, let's first drop our universal quantifier, and what we're left with is an unbound, two unbound variables, one that's attached to the predicate F in the antecedent and one that's attached to the predicate M in the consequent. And then what you want to do is swap out in that new sentence that you have gotten as a result of dropping the quantifier, swap out the individual variables, in this case x, swap them all out for an arbitrarily chosen name letter, something that names a particular individual in your scheme of abbreviation. So if you look up the top, we've got only two name letters so far. I'm going to add another one later. Lowercase c for copper and lowercase e for Ollie. So I'm just going to start by swapping in lowercase c. And the idea is to do this somewhat arbitrarily. Sometimes you have so many that you can't do them all mechanically, but just pick one and swap it in. And then the question is the sentence that results once you've swapped in a name letter true or is it false? So what is this saying? Well, what this is saying is that copper, if copper is a dog, then copper is a mammal. Well, is that true? It's a conditional. We know that it is true that copper is a dog. We know it's also true that copper is a mammal. Under what circumstances are conditionals true? Well, one of them is if both antecedent and consequent are true. So the conditional, if C is F, then C is M, has a true antecedent and a true consequent, so the whole conditional is true. So what we've just discovered is that that particular instance, which we got by removing the quantifier on the outside and putting in a particular name, that instance is true. Now, if every possible substitution of name letters for variables is true, then our original universally quantified sentence is also true. So what you'll need to do is then go in, one method is to go in and swap out the variable for the other name letter. And here we've got lowercase e for Ollie, so let's do that, and then we'll repeat the process and ask ourselves, is that true or is that false? And of course, Ollie is, like copper, both a dog and a mammal. And so both antecedent and consequent are true, so the whole conditional is true. And so it follows that that instance is true. Since those were our only two possible instances, What we've just discovered is that every possible way of substituting the variable for a particular name letter renders the resulting formula true. And if every possible substitution renders the formula true, we can conclude that the universally quantified version of that formula that had variables in it is true. Because what that says is that for anything whatsoever that you could swap in for these variables, for anything, if it is a dog, then it's a mammal. And what we just found by swapping in the particular name letters is that indeed it is true that for any particular thing, if it's a dog, then it's a mammal. Okay, what about this one? For all x, if x is f, then x is L. Now what is L? It's another predicate. It's one we haven't encountered. Let's look up at our scheme of abbreviation. And L is the property of being light brown in color. So whereas our previous sentence said every dog is a mammal, this one in English is saying every dog is light brown. Is this true or false? Well, let's go through the same process. First, remove the universal quantifier. Next, swap out the variables in the universal quantifier for an arbitrarily chosen name letter. We'll start with copper again. And then test it and think about whether it's true. Is it true that if copper is a dog, then copper is light brown? Well, once again, I should have put that picture of copper here again. If we look at a picture of him, he's both a dog and light brown, so the antecedent and consequent are both true, and so the whole conditional is true. All right, great. Now the question is every possible substitution instance rendering a true conditional? Well, let's make sure our universe of things is complete. Obviously not possible, and so this is hugely idealizing. I'm just going to add another name to our universe of names. Strictly speaking, that name should have been there from the beginning, but it didn't make it onto the slides. But usually you'll have a fixed set of names. So B is the name for Bo, which is one of the Obama's dogs. So let's try swapping in lowercase b for the variable x and do the same test. Is it true that if Bo is a dog, then Bo is light brown? Well, here's one of these is Bo. I don't know which is which. Maybe they're both sort of like really dark brown or black. I can't tell, but they're definitely not light brown, right? And they are both dogs. So what that means is that the antecedent of this conditional, Bo is a dog, is true, but its consequent, Bo is light brown, is false. And that means the entire conditional is false. Now, if you can find even one possible substitution instance of that universally quantified formula that turns out false, then you know the entire original formula was false, because it says that for anything whatsoever, any substitution you can possibly do. If it's a dog, then it's a mammal. Well, we just found something, Bo, that's both a dog and not a mammal. So it's not the case that if Bo is a dog, then, Bo is light brown, is what I should say. We just found an example of something that's a dog but not light brown. So we just found an instance of that universally quantified formula that's false. So we can conclude the whole thing is false. So the upshot is that if you are trying to test for the truth value of a universally quantified formula, only one possible substitution instance that is false renders the whole universally quantified formula false. And this makes sense because the universally quantified formula is making a broad general claim about everything. You only need one example that doesn't meet the criteria to show that that broad general claim is false. All right, let's try this one. This is an existentially quantified formula. There is some x such that x is f and x is L. What is this saying? In English, it's saying there is some thing that is a dog and is light brown, or some dog is light brown. How do we test for the truth conditions of a existentially quantified formula like this one? Well, similar to the procedure we use for universally quantified formula. We start by removing the existential quantifier. We're just left with these unbound variables that are conjoined with their predicates. And what you're then going to do is go in and swap out the variable for a name letter. And you'll do it with each of the name letters you have in your scheme of abbreviation. So here we've got 3, C for copper, E for Ollie, and B for Bo. And then the question is it true that it is at least one of those instances true? Do you have one substitution instance that is a true claim? Not, are they all true? At least one. So indeed, at least one of those substitutions there is a true conjunction. Because here's our substitution. C is F, which means copper is a dog, and conjunction, C is L, or copper is light brown. Well, copper is both a dog and he's light brown. Under what circumstances is a conjunction true? Well, only when both of its conjuncts are true, and that's exactly what we have here. So we know the whole conjunction is true. And if you can find even one substitution instance that's true, it doesn't matter what the truth value of the rest of them are. They may all be false. So for example, if you swap in lowercase b, you'll get something false here, because Bo is not a light brown dog. Bo is a dark brown dog. But that doesn't matter, because all the quantified sentence says is something is both a dog and light brown. Okay, on the other hand, what about a case where you have a sentence like this one? There is some x such that x is f, and it is not the case that x is m. Or some dog is not a mammal. Okay, how do we find out whether this is true or false, given our sort of universe of names and predicates that were given up there in our scheme of abbreviation? Well, we start as before, remove the existential quantifier, and begin swapping out name letters for the variables. Those are the 3 possible ways of swapping out the name letters. In each case, swapping out the variables for name letters. In each case, what we find is that each way of swapping in a name letter results in a false conjunction. How? Why is that? Well, let's look at the first one. The first one says copper is a dog and copper is not a mammal. Well, copper is a dog, but it's not the case that copper is not a mammal, because he is a mammal. So what we have is a conjunction with one false conjunct and one true conjunct. Well, that's enough to make the whole conjunction false. And of course, you can go down the list for E and B. Yes, both dogs, but they're also mammals, and so it is not the case that their M is false. And what that means is that under that circumstance, when every possible substitution instance of that conjunction, every way of swapping in name letters for variables, if every one of them is false, then and only then can you conclude that the existentially quantified version is false. So as a general rule of thumb, kind of just summing up here, it's much easier to make an existentially quantified formula true than it is to make a universally quantified formula true. So in order for a universally quantified formula to be true, every particular thing must meet the condition or conditions that are specified inside the brackets that the quantifier is operating on. If one particular thing, even one, fails to satisfy the conditions, then the universally quantified formula is false. On the other hand, in order for the existentially quantified formula to be true, all you need is just one particular thing that meets the specified condition. The only way for it to be false is if every single thing you swap in fails to meet that condition, or if nothing meets it. Okay. Thank you for your attention, and I hope this was helpful.